Did you know that local geologic and soil conditions can affect how you feel earthquakes? This phenomenon is known as side effects. In this video, we will learn what causes them, their consequences, and how civil engineers account for them in seismic design of structures. Before we start with side effects, let's recap some important concepts. In earthquake engineering, we characterize ground motions using several indices that correlate with damage potential, including amplitude, duration, and frequency content. The amplitude is usually described using the largest value of ground motion records. This can be maximum acceleration, PGA, maximum velocity, PGV, or maximum displacement, PGD. Duration indicates how long the structure is subjected to the ground shaking. Longer durations lead to cumulative damage. The frequency content refers to how the amplitude of a ground motion is distributed among different frequencies. This is important because structure responds differently depending on the frequency at which they are loaded. This can be seen in the following demo, where each lollipop represents a building with a different natural period. Remember that natural period is the time that it takes for a structure to complete one full cycle of oscillation. At low frequency motion, the tallest lollipop, the one with the highest natural period, undergoes the largest displacement. While at high frequencies, the shortest lollipop experiences the greatest motion. For the same excitation, we can graph the maximum response of different structures with respect to the natural period. This plot is called response spectra, and it is a convenient tool for seismic design. Now, let's see what are the key factors that influence ground motion. Ground motions are influenced by three main components: source, path, and side effects. Source effects are related to earthquake magnitude, which is a measurement of the energy released in the earthquake. Path effects refers to the propagation of seismic waves from source to bedrock beneath the site. In general, the amplitude of seismic waves decreases with distance. This is called geometric attenuation. The velocity at which the seismic waves travel depends on the stiffness of the ground. The softer the material, the lower is the wave velocity. Finally, side effects refer to how geological structures, such as geology, topography, and soil properties, influence ground motion characteristics. Local site conditions can amplify or de-amplify seismic waves, as well as modify the frequency content and duration of ground motion. Amplification is caused by the variation in the stiffness of ground materials. As seismic waves approach the surface, they encounter softer materials with lower shear wave velocities. For the waves to slow down, their amplitude must increase to maintain energy balance. Additionally, topographic irregularities such as crests or basins cause seismic waves to reflect, refract, and diffract, generating complex interaction that can lead to amplifications. The consequences of side effects can be catastrophic, as has been observed during recent earthquakes, including the 2023 Turkey earthquakes and the 2017 Puebla earthquake. The Turkey earthquake cost more than 50,000 lives and an estimate of $34.2 billion in losses. And the Puebla earthquake cost 220 lives in Mexico City, even though it was located more than 120 kilometers from the earthquake epicenter. The damage in Mexico City were a direct consequence of side effects. Most parts of the city lie on thick deposit of soft clay soils that tend to amplify seismic waves. This can be seen by comparing the acceleration records measured at two nearby locations with different soil conditions. The Tacubaya station, which lies on stiff soils, experienced a PGA of 1/3 of that recorded at SCT station, which lies on soft soils. The records also showed a change in the frequency content and an increase in the duration of the ground motion at SCT site. The topographic effects were also observed during this event. Most of the building damage during the earthquake were concentrated in transition zones between soft deposits and rocks. In these zones, the curvatures of basins induced stronger shaking and longer durations. Now that we understand what side effects are and the consequences they have, let's do a demo to internalize these concepts. For this demo, we will need a manually operating shaking table. In this case, we're going to use the Easy Shake Table from Pitsco. As an alternative, a link is provided in the description with a video of how to build your own shake table with widely available materials. Next, we need 3 structures with same characteristics. For this demo, we built 3 houses using magnetic sticks. As an alternative, you can use wooden sticks, straw, or even raw spaghetti. To represent different site conditions, we will use 3 types of sponges. The first is a dry floral foam block. This is a dense and rigid foam. We will use this sponge to represent a profile with high shear wave velocity, such as the case of rock. The second is a filter foam sponge. This sponge is more flexible than the first one, but is not too malleable. We will use this sponge to represent stiff soils like deep cohesionless material. Lastly, the third is a cleaning foam sponge with a very squashy texture. We will use this sponge to represent soft soils like soft clays or peats. Now, we're going to apply the ground motion to the 3 structures and observe the differences in the responses. What do you notice? Please pause the video and take a minute to internalize the differences you observe. Let's see it again. The demo shows how amplification and duration are modified for each type of soil columns. First, we can appreciate that the duration of the grind motion changes as a function of the soil type. Once the earthquake stopped, the rigid foam stopped vibrating right away, while the softer sponges vibrated for a longer time. The squashy, softer sponge had the highest impact on the duration of vibration. We can also observe that under the same ground motion, the relative displacement of the houses are different. The blue house, which sits on rigid foam, barely moved with respect to the table, while the displacements of the green and pink houses that sits on softer material were amplified. However, this is not always the case. If we apply different frequencies, we can see that amplification and duration effects change. This illustrates how complex side effects can be. Accounting for side effects in the seismic design of structures can be done using code-based design spectra and site-specific analysis. Seismic design codes usually provide design spectra, a smooth envelope of multiple response spectra representative of seismic hazard. Side effects are considered relating the structure response to an average soil profile characterization and incorporating amplification factors into the design spectra. The limitation of this method is that it assumes uniform soil conditions, neglects nonlinearity in soil response, and cannot capture topographic and basin effects. Site-specific studies aim to obtain a predicted ground motion at the outcrop of the site accounting for specific characteristics. This can be done using ground response analysis that can be based on equivalent linearizations and non-linear analysis. The limitation of these methods are that they require a good characterization of the site and that models should be used with special care considering their respective assumptions. The selection of the analysis depends on the amount of information available, the type of structure, and the level of accuracy required for the design. In this video, we learned that local site conditions such as geology, topography, and soil properties can change the characteristics of ground motion, including amplitude, frequency content, and duration. This side effect ultimately affects the seismic demand of structures and have caused significant damage in the past. As civil engineers, we have different techniques to account for side effects in the design of structures. Accounting for them in the seismic hazard definition is key to design safe and reliable structures and mitigating earthquake impacts.